we go along. Thank you very much. Ethan?
Yeah, thank you so much for the introduction, Jennifer. She said, my name is Ethan Partington. I'm a PhD student in the Physics and Astronomy department. Specifically, I am doing my dissertation on the gas that travels around the supermassive black holes at the centers of every major galaxy. So while there are supermassive black holes at the center of every major galaxy, and about 1% of the time when we look out in the sky, we would say that a galaxy has an active nucleus. That means that there is either a star or a cloud of gas that has passed close enough to the center that that gas is now being gravitationally pulled towards the center of this black hole, where it then whips around at relativistic speeds. That just means near the speed of light, so incredibly fast. And as you might remember, if you've taken an intro electromagnetics course before, if you take charged particles like the ionized gas out in space in nebulae or in the outer layers of stars, you take those charged particles and accelerate them to extremely high speeds, you're going to get a ton of energy out. So that is the energy that I study. It's one of the most sort of energetic processes in the galaxy or in the universe that we know of. So any galaxy questions you have specifically about black holes or about their formation and evolution, as we go through this talk today, feel free to shoot your hardest questions at me. I love questions that sort of make me, dive deep into my physics knowledge. So feel free to hit me with those. Just pop them in the chat. As Jennifer mentioned, I'll take some breaks to ask or to answer questions if there are ones that are particularly relevant to the talk. And then all of the other ones I'm happy to answer afterwards. So any sort of general astronomy questions, feel free to submit those as well. So just a little bit of a overview of the talk today. So first, we're going to fly to the Virgo cluster. This is a very densely packed cluster of galaxies in our nearby neighborhood. We're going to talk a little bit about how galaxies form and the different types of galaxies we see in the sky and what that can tell us about their history and their physical characteristics. Then we're going to take a look at the nearest galaxy to us. This is the Andromeda galaxy in our local group. Finally, we'll take a look at the location of our own galaxy's supermassive black hole. As you might expect, black holes are black. They don't emit light. The reason that they're so sort of dark is because their gravitational fields near the center are strong enough that not even light can beat the escape velocity required to sort of break out of their gravitational pull. So unless you get an active nucleus, like the one that we would see in one of the galaxies that I would be studying, which is unfortunately not the case for Sagittarius A Star at the center of our galaxy, there's not really going to be much visually to look at, but it is cool to be able to, go out in the night sky tonight and be like, hey, that's where the center of our galaxy is. So I'll show you how to find that as well. Finally, time permitting, we're going to fly to the Milky Way's very own satellite galaxies. Down in the southern hemisphere, you can see the large and small Magellanic Clouds, which are sort of a different class of galaxy that is known to sort of lurk around larger galaxies in the outskirts. So we'll be looking at all of those today. I've got some questions for the audience that I have prepared. So I will make that very clear when I'm asking one of those. And I'll just ask you to pop your answer down in the chat below. So without further ado, let's go ahead and get started. The first thing that I wanted to show everyone is, before we get too far out into deep space, a few of the objects that you can see with the naked eye tonight at sunset. So this is the sky overhead in Detroit at about 9:46 p.m. The mountains are just wishful thinking, but this is just the same latitude as Detroit, same longitude. So the sun will be setting around 9:45, and right on the western horizon, right after the sunset, you'll see this little dot in the sky that's sort of very, very close to where the sun was setting. This is our neighbor planet Venus. Venus is often referred to as either the morning star or the evening star, depending on whether it's to the east or the west of the sun. Right now it's in its sort of evening star phase where it's trailing the sun. This is the brightest object in the night sky after the moon and sun, of course. So keep an eye out for that one. This will be a great way to help you get your bearings, because this is pointing due west in the sky. Over in the southeast, we have our beautiful moon. The moon is in the waxing gibbous phase. One of the best ways to tell the difference between whether the moon is in the waxing or waning phase is where it is in the sky at sunset. If it's overhead when the sun is setting, that means that it is approaching the full phase, where it's on the opposite side of the sky from the sun, on the or waxing, meaning that it is getting brighter in the sky. The waning phase will be seen late into the night, towards the early morning, because the moon has now moved right to the other side of the earth, so it is nearer to the sun at sunrise. So those are the two biggest things to keep an eye out for tonight. And then I'm going to move us forward just a little bit past sunset so the sky can really darken. And I'm going to show you a couple of constellations that we're going to use to help us find the Virgo cluster, that first target full of nearby galaxies. So I'm going to move us forward in time to about 11 o'clock p.m. This is when the sky starts to get really dark. And one thing that you'll notice over in the east that has begun to rise is this sort of milky or cloudy region in the sky. This is very difficult to see if you're in any sort of urban or suburban environment. So this is really going to be one that people sort of see in the planetarium. They expect to see it during their, trip out to Warren or Southfield, and then they're sorely disappointed when you don't get to see this beautiful structure. But if you go up to a dark sky site, you should actually be able to see this sort of arm of the Milky Way quite clearly. One of the interesting things that sort of keys us into the orientation of the galaxy is, one, the direction of these arms, and two, how it gets sort of brighter near the south and fainter near the north. What we're looking at when we look towards the south in the constellations of Sagittarius the Archer and Scorpius the Scorpion is the center of our galaxy. So if you've got a keen ear, you may have picked up on the fact that I called the center of our galaxy Sagittarius A Star. It's right along this sort of edge here, which makes the arm drawing back the bow on the archer. And this region, as you can see, we can't see the giant black hole at the center, but what you can see is the starlight from the millions of stars in what we call the galactic bulge. This is where the gravity from this black hole's, the gravity from this black hole is strongest. If you recall from the solar system show last month, you may recall that gravity is an attractive force between objects with mass. So any objects that you can pick up and put down are going to have mass. The more massive the two objects are, the stronger their gravitational attraction, and the closer they are together, the stronger their gravitational attraction as well. So as you get close to the galactic center, where you've got the mass of this supermassive black hole, you're going to get a ton of stars clustered around it, sort of in this very tight orbit. So that is the light that we're seeing over here in the southeast. Now, these stars are tens of thousands of light years away. They are not close by any means, which means that rather than the sort of individual pinpricks of light that we see from stars in our nearest sort of 1,000 light years or so, we're just seeing the sort of diffuse emission from all of these stars combined as it gets scattered through what we call the interstellar medium. The interstellar medium is all this gas that's making these sort of wispy trails in the sky. Some of them are a lot colder and more opaque, and that's where we get these dark lines from. And then the more translucent or thin and hot gas is where we're actually getting that light scattering effect from. So that's the first sort of notable feature that I wanted to point out in the sky. And the next one is going to be this very bright constellation in the north. This is the constellation of Ursa Major, or the Great Bear. She's also well known as the Big Dipper, or the Drinking Gourd. This is a group of 7 very bright stars and then numerous other faint ones that, when you put them together in the sky, make a bear with a very long tail. This comes from the historical relic of this Greek myth, where these were people that were turned into bears and then flung up by their tails into the sky by the king of the gods Zeus. Zeus, in flinging them up into the sky, stretched their tails out, hence this handy explanation for why these bears' tails are so darn long. Then we have the rear paws, front paws, neck, and nose of Ursa Major. And if you take the shoulders of Ursa Major, the Great Bear, or the edge of the Dipper, if we follow this sort of trapezoid shape to be the scoop of the Dipper, and then the tail to be the handle of the Dipper. If you follow either Ursa Major's shoulders or the edge of the Dipper and continue outward in the direction that the Dipper opens, about 20 degrees or 2 fist widths stacked together. 10 degrees is about 1/18 of the sky. We've got 180 degrees in the sky from east to west. If you extend your hand out at arm's length and close one eye, from your one side of your palm to the other, it's about 10 degrees. You can use that as a measurement for amateur stargazing. Astronomers do it all the time, especially it's very convenient because everyone's palms are roughly proportional to the length of their arm, meaning even if you've got a really small arm, your palm will often be smaller in correspondence, meaning that you still end up taking up about 1/18 of the sky with the width of your palm. So 2 palm widths across in the sky will get you to Polaris, the North Star. This is in the constellation of Ursa Minor, or the Little Bear. And this is sort of one way that we use the Big Dipper as a directional tool. This is the more commonly known one because for navigators and survivalists and travelers, even dating back to people on the Underground Railroad and way before that with early celestial navigation, this trick has been useful for people trying to find their way north. But there's another trick that's helpful for astronomers that I'm going to point out to you now, which is using the tail of the Big Dipper. So if we go back over to Ursa Major and we follow the arc of the tail about 20 degrees out, along that arc, you get to the star Arcturus. So a lot of the times you'll see people say arc over to Arcturus, and then the next step on this train to try and find Virgo for the Virgo cluster is to continue downward in the direction that we found Arcturus for about 20 more degrees until you get to Spica. Sometimes you'll hear this as arc over to Arcturus and then spike over to Spica. I'm not a huge fan of saying spike over to Spica because that always made me think that you had to make like a huge angular change. But if you go back down, if you go down further towards the southern horizon, you'll get to Spica. One of the cool things about these stars in this part of the sky, which is known as the the spring triangle, completed by the star Regulus in the constellation of Leo the Lion, is that each of these stars is a different color. So a star's temperature is directly correspondent to its color, with red stars being cooler and blue stars being hotter, much like if you were to look at a flame, right? The blue light at the center is hot, and then as you get closer to the air surrounding it, you're going to get cool and red. This is something you can really see, especially on a clear night. You'll see that these stars all sort of twinkle between white and their true color. So Arcturus in the constellation of Boots, the shepherd, he's this little sort of kite-shaped man here that's sort of driving the bears across the sky. Arcturus is the brightest star in Boots. And then Regulus is the brightest star in Leo the Lion. Leo is best known for this sort of trademark question mark shape. And then, oh, we have a question. Does the change in color for stars refer to variations in their gaseous structure? Yeah, so typically, this is a whole different talk that I would love to do a stellar evolution talk at some point. I won't go super in depth on this now, but essentially the amount of mass the star has typically defines it does define its starting temperature. So a star with more mass is going to be able to burn through its fuel faster and it's going to run a lot hotter. A star with less mass is going to be much cooler because it's not glowing as brightly, just like how a big fire will be a lot brighter, right? In this case, we also have, if you add like gasoline onto your fire, it's going to have a lot more fuel immediately accessible, and it's going to burn a little bit more blue. So that's what we see with these. And then you actually can get lifetime changes in the star's color based on its age. So especially for stars like Spica, which is a blue giant star, as it gets older, that means it started out with a lot of mass and it's going to be burning very, very hot for the first like 90% of its life. And then as it gets older, it's going to burn through its hydrogen fuel supply and eventually start burning heavier elements, which gives it less energy. And what that means is that the structure of the star is going to sort of change. It's actually going to expand, and then it will cool off from that subsequent expansion. So yeah, great question. So once you've found the spring triangle, you're ready to look for Virgo, the goddess of the harvest. Now, the reason that I have people find Boots the shepherd and Leo the lion first is because these constellations are made up of a lot more bright stars. Virgo, on the other hand, pretty much has Spica and then a bunch of other faint ones. So Virgo is the goddess Demeter. That's what she sort of became appropriated as in the Greek mythological sky. And Spica is the sheaf of wheat that she's holding as she sort of harvests the grain from the fall. She is depicted as the sort of woman standing upright, holding her grain. And I can give you a quick view of what that actually looks like if you'd like. I find that overlaying the images of sort of the mythological view of these constellations sort of helps when picking out their shapes in the sky. So here we have Virgo, the goddess of the harvest, accompanied by her other friends that I've mentioned. And right now, I'd like to tell you the story of Charles Messier, who was an 18th century astronomer. This was after Galileo first used the telescope in the 1600s to look at the sky, but before we really had sophisticated observing equipment that allowed us to observe the more faint objects in the sky. So Charles Messier was coming into astronomy during a time when astronomers were very concerned with the layout of the solar system. We had just about 200 years ago, or 200 or 300 years ago, definitively proven that the sun was the center of the solar system. And now we had already found two new planets, Uranus and Neptune, and a slew of comets and asteroids and other local objects. So although Charles Messier is best known for the Messier catalog, which includes many of the galaxies that are visible with the telescope to amateur astronomers, he was actually not setting out to be a galactic astronomer. That wasn't even a thing at this point. He was simply looking for objects that looked like comets. Comets are best known for their distinct halo, as ice from the rocky comet is melted off and vaporized as the object gets closer to the sun. So he was looking for objects that had this sort of vapor-like or nebulous structure to them, but he found a lot of objects that weren't moving as quickly as he predicted comets would. They were sort of stationary with respect to the background stars. And many of those were in the constellation of Virgo. He classified these with the numbers 1 through 115. So for instance, M87, the largest galaxy in the Virgo cluster, which we'll zoom in on now, was Messier 87, the 87th object that he found. So let's go ahead and magnify in on M87 right now. And while we're doing that, we can take a look at some of the other galaxies in this region as well. Anything that's got this sort of like blurry shape around it is a galaxy. Anything that's sort of this discrete concrete circle, that's a star. So it can be very you can imagine how disorienting it was for him when he was trying to figure out what these objects were, because they're often comparable in brightness to nearby stars. They just have a completely different structure. So rather than really investigate these further, he was limited by his observing equipment at the time, and they really all looked like little blobs. He basically wrote them down in a catalog with their locations so he wouldn't accidentally stumble upon them again, and went about his merry way looking for comets. Now, a couple decades later to 100 years later, especially in the 1900s, when astronomers are developing these really big upright telescopes with these massive lenses and mirrors, astronomers come back and revisit the Messier objects and find that a lot of them have very distinct physical structures. So the first one that I want to show you in this is actually M90. It's one of the constellations in this group. So we're going to magnify in on it. And this one you'll see has, in addition to this sort of wispy or nebulous literally just means like sort of diffuse and gaseous. So that's where the term nebula comes from. This was initially classified as a spiral nebula due to these sort of spiral arm structures. But as astronomers measured the distance to this object, they realized that it was millions of light years farther away than any of the stars we were detecting in our galaxies or inside of the Milky Way. They found dozens of these objects, and all of the objects in this cluster and several others throughout the sky were all getting these absolutely incomprehensible distances that were orders of magnitude higher than the stars and the other nebulae that we were finding inside of our own galaxy. So this is where the theory for galaxies started to pop up, that maybe we weren't in this big homogeneous spread of stars that just went off infinitely. Maybe there was a boundary to our galaxy and then some empty space, and then subsequently all of these other galaxies floating around that just appeared very small because they were extremely far away. So my first question to you of the evening is, which do you think was formed first, stars or galaxies? And to help you inform your question, I'm going to have you come up with a definition of a galaxy, for instance, just in your head. You don't have to type it out, but come up with sort of a loose definition for, you know, what is a galaxy based on the stuff I've said. And then do you think that the existence of galaxies requires the existence of stars or vice versa? Roger asks, how close to each other are stars in the galactic center? Let me look up the average distance of them, because this is something that has been sort of recently studied more and more. It was pretty hard to resolve all of the stars in the center, like spatially, until about the 90s. And then over the past 20 years, this one group that won the Nobel Prize in 2018, or no, in 2020, sorry, last year, Andrea Ghez and her team, they sort of published a bunch of findings on the motions of these stars. So I can look up the distances between them if you'd like, because I don't know it off the top of my head. And I will post my question in the chat. Y'all can just type your answer in, whether you think it's the stars or galaxies were formed first. All right, yeah, so it looks like in the center of the galaxy, stars are about, they go from like 0.1 to 0.01 light years apart. So for comparison, the minimum distance is about, off the back of my head, I would say about 6 to 10 times the distance from the sun to Pluto. So quite close in astronomical distances. 0.1 light years is extremely close, especially when you consider the separation of stars in the outer wings of the galaxy. At the very end, I can show you guys a schematic of where we fall in the Milky Way. And you'll find that out here in the outer arms where we live, you're gonna be, you know, a few to tens of light years away between each star. So for instance, the Alpha Centauri system, which is the nearest one to us, is 4.2 light years away. So they are like 10 times closer together at the center. All right, it looks like most people are agreeing that stars were formed first, and this is correct. So let's zoom out so we can get a nice little view of more of the Virgo cluster as well. So just to give you sort of a quick overview of the moments after the Big Bang to the first billion years, the Big Bang was the first sort of record we have of the universe, right? This is when the universe rapidly expanded and we see the formation of the first subatomic particles. So this, it takes about 370,000 years for the first subatomic particles to form. And during this period, you get a huge explosion of light as nuclear reactions are taking place. You have antiparticles and particles annihilating each other, which releases light. You have fusion reactions happening, or you don't have fusion reactions happening, but you have protons and electrons decaying from neutrons, which releases light as well. So all of this light coming from particle physics interactions. And then for about 200 million years, the universe enters what we call the dark age, because after all of this particle formation happens, everything is now slowly moving under the influence of gravity. So now all of these objects, which are no longer radiating light, are slowly moving in towards more dense parts of this just big hydrogen gas fog. Essentially, anytime you get a part of this hydrogen cloud that is the universe that is more dense than another region nearby, it begins to compact in on itself under its own self-gravity, and then that dense region will pull or attract gravitationally the other objects around it. So it takes about 200 million years from sort of the settling down of all of these particle interactions to the first stars being born. This is where these gas clouds are getting dense enough in specific regions, and they've compacted enough material that at the center of these protostars, the temperatures are reaching millions of degrees, meaning that hydrogen atoms are being accelerated together at speeds where they can collide and form the first helium atoms. So this is what we call a fusion reaction, when the two hydrogen atoms force together and collide, merge their nuclei into a new atom. The subsequent mass of the helium atom is a little bit less than the sum of the two hydrogen atoms, which means that some of that mass has been converted to energy following Einstein's equation, the E equals mc squared relationship. So the change in mass times the speed of light squared is equal to the change in energy. And this produces a ton of energy, more than anything we can access here on Earth. It is beat by the accretion of gas onto a black hole. If anybody wants to know about how we discovered supermassive black holes at the center of galaxies towards the end, I'd be happy to go into detail on that. And essentially, this is one of the most energetically efficient reactions we know about, and this is enough to power the heart of all of these stars that are beginning to form. Now, over the next 800 million years or so, we're approaching the first billion years of the universe. So its 1 billion year anniversary is coming up. And by the 1 billion year anniversary, we now have our first galaxies. So while these stars are forming, there are also, we believe, a bunch of primordial black holes. These are parts of this sort of hydrogen fog cloud that collapsed too rapidly for any sort of internal pressure to sort of equilibrate out and stop the collapse from happening, meaning that in these little regions that collapsed too rapidly, we now have a singularity, or an object of infinitesimally small size. These are the primordial black holes. You have lots of scientists today that are trying to detect these primordial black hole mergers. And one of the reasons that we think they must exist is because this is sort of the best explanation we get for the mass of the supermassive black holes at the centers of these galaxies. So typically, stellar mass black holes that are formed at the end of a star's lifetime are between 8 and 10 solar masses. You get lower, or between 1 and 8 solar masses, because a lot of the material in the stellar environment gets sort of blown away by the supernova. So you see a lot of black holes that are around 1 solar mass, and 1 to 10 is sort of the low mass range. Then you end up with these supermassive black holes at the centers of galaxies, which are, for instance, Sagittarius A Star is 2.6 million times the mass of the sun. So just statistically, it's going to be extremely hard to generate these supermassive black holes just from sort of coalescing of stellar mass black holes at the end of a star's life cycle. We also know that it only took about 800,000 years for the first stars to form, and then after that, the first galaxies to sort of develop their structure around these supermassive black holes. So that's not enough time to produce this much mass from a stellar evolution pathway perspective. So that's where the idea of primordial black holes come from. Our best idea is that these primordial black holes were forming in this early part of the universe out of some of the hydrogen gas that collapsed too quickly, and then those began to merge. They in-spiraled together, leaving tons of gravitational radiation. So we would expect to be able to see gravitational waves from these primordial black hole mergers. And they merge, they sort of snowball out of control until you get these ones that are millions of times the mass of the sun. And that is what sort of serves as the anchor to these galaxies. So what this means is just like the sun sort of formed, and then you end up with this gas that's sort of attracted to the sun, and that sort of coalesces into the gas giants, and then the little rocky regions that are very close to the sun coalesce into the planets, and then all of that stays in an orbit around the central object. We get sort of a similar thing happening with these galaxies. So we have this supermassive black hole that draws in the attention of a ton of stars in the nearby region. Like we were talking about, these stars get extremely close together, and that's where we get the sort of galactic center bulge at the center of these galaxies. You can zoom in on our friend M90 that we were just looking at and see very clearly this stellar bulge that happens. Then the combined mass of the black hole and these central stars begins to attract stars that are further out in space, and they get pulled into the outer arms of this galaxy. Now, during this time, we're also about to approach what's called the inflationary period of space, or of the universe, which means that much like if you drew two little dots on an uninflated balloon and then it blew it up, these dots don't really, nothing's like, you know, strapping rockets onto the dots and sending them flying away. Rather, space itself, or the fabric of the balloon, is expanding, forcing these objects, these galaxies, to become extremely sparse and separated in space. So that's what we begin to see after the first galaxies form, which is why there's so much empty space in between them. So I once had a really good question, which was, do new galaxies form? Like, when was the most recently formed one? And the answer to that is, after the first billion years or so, we kind of have our fixed number of galaxies. You see a lot of them end up merging together, which I will talk about in just a second when we fly over to M87. But for the most part, unless two galaxies merge together, we're pretty much stuck with the same amount of galaxies that we had a billion years after the Big Bang. So next up, let's zoom in on M87. This one is special because 2 years ago in 2019, this was the first black hole that was ever directly imaged, which was a really, really cool thing for astronomers. This was using the Event Horizon Telescope, which was an interferometer that was composed of several telescopes all across the world, all observing this object at once, sort of creating effectively an observing area the size of the surface of the Earth. So really massive science project that happened 2 years ago. And that allowed us to take a picture of the accretion disk around the very center of M87. So M87, you may notice, is a little bit different than the rest of the galaxies that you might look at in, say, you know, prettygalaxypictures.com or M90 that we just looked at. And the reason for that is because it's missing those trademark spirals. So this is what we call an elliptical galaxy. This is something that happens a lot of the time after one of these galaxy mergers. There's sort of two really good indicators that a galaxy merger has recently happened. One is that the spiral arms are no longer there in a sufficiently massive galaxy. The other one is the presence of an active galactic nucleus. That was the phenomenon I mentioned earlier, where you get gas or a star moving too close to the center of the black hole, and it gets ripped apart and sort of forms this accretion disk, or this disk of hot glowing gas around the supermassive black hole. This is what allowed us to directly image M87. If you look at pictures of this black hole, you'll notice that it's sort of this dark region in the center surrounded by this red gas. The gas is the accretion disk. And the reason that these mergers produce both of these features is sort of like if you were to, you know, mix wet goods and dry goods for a pancake recipe, right? You would see initially that you're going to have these very clean sort of lanes of the flour versus the water and oil. But the longer you stir it together, the more homogeneous it's going to become, right? So that's where we get these sort of spiral structures that get disrupted as the two galaxies travel close together and end up in this sort of gravitational mixing dance, where the nuclei of the two galaxies will sort of orbit around each other until the nuclei eventually coalesce at the center. At the same time, this means that these nuclei are moving a lot more than they usually would. A nucleus is just the supermassive black hole. What that means is it's sort of sweeping through all of this space dust, right? Everything that makes up the interstellar medium is now sort of getting plowed through by this black hole. Two of them, in fact, one from each of the host galaxies. And that means that you're going to get a ton of chances to pick up an accretion disk. So a lot of the times when we look at active galactic nuclei, we can tell that these are galaxies that have recently merged. I read a paper recently, which was really fun, where a group of scientists actually found what they call a double active galactic nucleus, where the two galaxies had merged quickly or more recently enough that you could actually see two galactic centers, each of which had their own brightly glowing disk. So M87 was a great target for the black hole imaging effort, not only because it was an active nucleus, but also because this is the largest black hole in our region. This one has a mass of, let me pull up its exact mass because I never remember it off the top of my head, 6.4 billion solar masses. So like everybody on the Earth can have their own chunk of this black hole that is one solar mass. It is 2,200 times more massive than the Milky Way's supermassive black hole. So this is an extremely large galaxy. As you can imagine, the size of the sort of galactic halo or all of the rest of the stuff in the galaxy is a lot larger as well. The more massive your nucleus is, the larger your galaxy is going to be typically. There's one other galaxy that I wanted to show you in the M58 region, just because I think it's a beautiful example of or in the Virgo cluster region, just because I think it's a really beautiful spiral galaxy and it gives you a really good chance to look at what a really clean spiral structure looks like. And while we look at that, I'm going to explain to you how elliptical galaxies can occur naturally, because what we do find is a lot of very tiny galaxies are elliptical as well. And so we've sort of realized that, all right, spiral galaxies are formed in much the same way that the proto-solar system disk was formed, where you have all of this gas surrounding the sun, and this gas sort of coalesces into little planets, or planetesimals rather, the sort of proto-objects that then combine to form the planets we see today. And as those all interact gravitationally, they're going to conserve angular momentum, and they're going to sort of bump or collide into each other along the sort of axis perpendicular to the cloud's original spin. And as they bump, they're going to cancel out that vertical motion and only keep the sort of horizontal angular motion around the direction that the cloud was originally spinning. We see this in solar systems, we see this in moon systems as well. That's why, and we see it in ring systems. That's the same principle that guides Saturn's ring structure being so thin, right? It's just conservation of angular momentum. And so for large galaxies that have a bunch of stars, they're able to do the same thing. As they interact for a billion years or so, they're going to sort of condense down into this flat plane. And in the flat plane, they're going to sort of stratify into these little wings or spiral arms as more dense clusters of gas will sort of clump together under their own self-gravity. Now, some galaxies, when we take a look at dwarf galaxies in a minute, you'll see that not all galaxies have this spiral structure. A lot of them look like very small versions of M87, that elliptical one we looked at. And the reason for that is just that they didn't have enough material, not enough stars to sort of condense into that spiral looking plane. So if you see an elliptical galaxy, the chances are it is either a product of a merger or it's a dwarf galaxy that was just too small to form a spiral structure. So my next question for you all, if we zoom out, is then what structure do you think the Milky Way is? And I'll give you a hint. You can use the sort of view that we get from inside of our galaxy to figure out whether it's a spiral galaxy, which is roughly flat, like a big pancake, or whether it's an elliptical galaxy, which is sort of like a big egg with stars all moving in all sorts of crazy directions. So Elise asks, do galaxy spirals always go in the same direction? No, they don't actually. It's an excellent question. So the galaxy's spirals just depend on sort of what spin or kick the original cloud of stars that sort of moved around the black hole had. Typically, the spin of the black hole will then pull stars that are moving in that same orbit. One thing that you'll see in what's called retrograde orbits, where an object is spinning one way and then its orbiting body is orbiting the other way, is that actually produces a little bit of gravitational friction, we call it, as the objects are sort of constantly trying to pull away from each other's faces. It's a lot easier to spin the two objects in the same direction. We've got a moon around Neptune called Triton, which is in a retrograde orbit, which means someday it will end up infalling onto the planet. So everything in one galaxy will end up typically moving in a prograde motion aligned with the spin of the supermassive black hole. Otherwise, it would start to decay and fall inward. But galaxies' individual spins end up being pretty independent of one another. You can look at two galaxies in the same cluster and they'll appear to be spinning in different directions. One other thing to point out is that the orientation that you view a galaxy with sort of determines how flat it's going to look, right? So we looked at M87, the elliptical one, would kind of look the same no matter what orientation you were looking at it with. But M58 or M90, if you looked at them directly on their side, they would just look like a little line. Oh, and Roger asks, why did the earliest universe have areas of greater density enabling stars to form? It's a good question. So it's sort of just due to the random assortment of hydrogen molecules around. Like, let's say you grabbed a handful of rice and dropped it on your table. If there are kids listening, don't do this without your parents like telling you you can do this. But what you'll see is that some of the rice will fall in slightly more close together clusters just due to everything having an equal probability of landing somewhere. The odds that everything is going to be completely homogeneous, right? Every rice grain is going to be exactly 1 millimeter apart from one another is actually highly unlikely because you've got everything sort of landing on the table in all sorts of different orientations with their own sort of random momentum kicks when I release the thing. So what would happen in this sort of demo is then you would group all of the rice that's in the denser clusters together into their own little like pouches and collect any rice that's nearby them. And that's how we get material that forms these stars and primordial black holes. Fantastic question. Thank you, Elise. I accidentally sent a DM to you instead of everyone. So to everyone, my next question while we're moving to sort of the next part of the lecture is, what type of galaxy do you think the Milky Way is? And while you're deliberating, a barred spiral just means that there is a bar in the center of it, which means that the central region is a lot brighter than like over a large region of space rather than just being like a really small little circle. And then while we are taking a look at that, I want to show you how to find our nearest galaxy. This is the Andromeda galaxy. So one of the lovely things about living up here in the north is that we have a lot of north circumpolar constellations, which means it actually is a lot easier to learn the sky up here because a lot of the constellations in the north just kind of hang out up there year round. I went to undergraduate school in Georgia, so when I was working there, I had an extra 10 degrees of sky to memorize. But coming up here, you should be able to see the Andromeda galaxy for a good portion of the night. We're gonna have to go a little bit later into the evening for it to be visible right now. So right now the sky is at 11 p.m. I'm gonna go forward to midnight. Fun trick you can do as well while you're watching this is a really good way to sort of see why the North Star is so useful for navigators. Since it's directly above the Earth's axis of rotation, as we spin around in the sky and go an hour ahead, everything's going to appear to rotate around Polaris. North circumpolar just means it's in this circle around the North Pole that's always above the horizon. So let's go forward in time just a little bit. Perfect. This is a little bit closer to 1 a.m. And then as we get further into the summer, the Andromeda galaxy will be rising earlier and earlier. So we're actually going to use we're going to use the Big Dipper one more time to find another galaxy. So what we can do, and a final note about the Virgo cluster, it's in the center of that sort of box-shaped body of Virgo. So one thing that I love to do when I've got a telescope or binoculars is just point my telescope at a random chunk inside of this box and see how many galaxies I can find. Sort of do Charles Messier's bit that he did when he was making the Messier catalog, but 300 years later. So the next thing to do is find the Big Dipper. And we're going to continue outward in the direction of the Dipper's sort of scoop towards Polaris and then the constellation Ursa Minor. And finally, we're going to settle on the constellation Cassiopeia. So this is about 40 degrees away from the entrance to the Big Dipper. So 4 hand widths stacked. You can put 2 hand widths in between Ursa Major and Ursa Minor, and then keep going from Polaris to Cassiopeia. And Cassiopeia is this W shape. If you get out into the countryside, you'll see that it's directly in the plane of our galaxy. Speaking of the plane of our galaxy, it looks like most people agree that we are a spiral galaxy. That's correct. An elliptical galaxy would mean that we would be seeing sort of this hazy, starry, milky area all over the sky. Rather, instead, we are sort of constrained to this one region. Now, the Milky Way galaxy is not completely flat, right? It's not as thin as, say, Saturn's rings. There's some puff to it, and that's why we're able to see stars in all directions in our near neighborhood. But as we start looking very far away, we're going to see everything sort of condensed to the horizon. Just like, if you were looking around you, you might see leaves up above you, in a forest. Or on a mountaintop, you'd see the leaves above you, you'd see trees sort of appear to be in all directions, you could find leaves anywhere you looked, and then as you look outward into the forest farther and farther away, everything's going to sort of settle down on the horizon. So when we find Cassiopeia, the next thing to do is I like to look for this equilateral, or the closest to equilateral part of Cassiopeia's body. These are her legs sitting on her throne. She was the queen of Ethiopia, and she was put in the sky as a cautionary tale about vanity. She's one of my favorite myths. So if anybody wants to hear that at the end, I'd be happy to tell it briefly. But if you take this sort of triangle and point outward in the direction of the sort of bottom of the W, then you go about 15, 20 more degrees, and you'll get to this line of stars called Andromeda. Andromeda is the daughter of Cassiopeia, and the Andromeda galaxy is named in her sake because, as you'll see, most of the constellations, then when you find a deep sky object in that constellation, you simply name your object after its host constellation. So in between Andromeda and Cassiopeia, about 2/3 of the way out from Cassiopeia, you'll see this sort of smudge-like shape in the sky. It doesn't look like it's quite part of the Milky Way, but it's got a sort of similar hazy tone to it. This is an entirely different galaxy that we're seeing. It's visible with the naked eye if you get to a dark part of the sky. So I'm going to zoom in on the Andromeda galaxy, and I'll tell you a little bit about our nearest neighbor. So the Andromeda galaxy is another spiral galaxy. She is about twice the diameter of our own. So the Milky Way is about 100,000 light years across, and she is about 200,000 light years across. This galaxy is extremely far away. She's 2.9 million light years away. So right, for comparison, the center of our galaxy is about 26,000 light years away. This is much, much larger, orders of magnitude farther away, but this galaxy is large enough that you can still see it with the naked eye. So these are really massive collections with billions and billions of stars. The center of the Andromeda galaxy, has a supermassive black hole that weighs about 200 million solar masses, so about 100 times more massive than our black hole. So you can see an increase in about 100 times the mass of your central object yields you about double the size of your galaxy. we've got a dwarf galaxy orbiting around Andromeda. This is another one of those tiny elliptical galaxies. So rather than being the product of a merger, we instead see this is just sort of one of those small ones that wasn't able to pull itself into a disk like Andromeda or the Milky Way. There's one other galaxy in our local cluster called the Triangulum galaxy that's a little bit smaller than Andromeda. But other than that, our nearest neighbors are all some of these dwarf galaxies that don't have a disk structure. The last thing that I want to mention about the Andromeda galaxy is that I've been talking about mergers all evening long, and this is actually going to be part of a merger someday with the Milky Way itself. So in about 2012, this group of Harvard astronomers were observing the sort of radial motion of the Andromeda galaxy by looking at the blue shift of the emission lines from gas clouds in this galaxy. And what they found is that it's actually accelerating towards us. So it's sort of charging on a collision course with the Milky Way. This was pretty unexpected because we weren't sure whether these two objects were gravitationally bound at the time, but they just happened to be going at the right velocities and in the right directions, that in about 4.5 billion years, the two are going to merge. This is going to be a pretty safe event here on Earth. The likelihood of any two stars colliding or interacting with each other's sort of stellar atmospheres, the bubble that sort of solar wind that keeps us from getting interfered with by the interstellar medium. The likelihood of anything disrupting our heliosphere is like less than 1%. It's basically not going to happen because space is so empty, right? You can fit 4.5 light years roughly between us and our nearest neighbor. So more likely, stars are just going to be sort of whizzing in between all of this existing empty space. At the center of the galaxy, things are going to get a little bit more crazy. I would personally love to travel into the future and see if we get a double active galactic nucleus as these two black holes sweep up a bunch of material around them. But eventually, after this merger happens, the spiral structure of both of our galaxies will get obliterated. The two supermassive black holes will merge at the center. And finally, we will get this new elliptical shaped Milkdromeda galaxy. So that's going to be something to keep an eye out for if you're able to live forever, for instance. The next thing that's sort of interesting in the astronomical time scale that we're looking at is in 5 billion years. That's when we predict that our sun is going to reach the end of its life cycle, and it will begin to expand out past the orbit of Earth. So that, just like we were talking about earlier, when stars age, their interior composition sort of changes. They get a lot less dense and they also cool off. So you'll have a cool 500 million years in between the Milkdromeda merger and us having to get off of this planet and somewhere safer. So that is the Andromeda galaxy. This one you can see with the naked eye. I've found it several times and on particularly dark, clear nights. But this is a great one to impress people with if you've got even a pair of binoculars. The best thing to do is to bring a little green laser pointer with you and bring a little star atlas. The great thing about star atlases is they have the constellations in the sky that you're in the region that you're looking at, and then they'll have little circles that show where cool deep sky objects are. So you can sort of say, oh, okay, it's on these lines between these two constellations, and just sort of scan the night sky with your eyes or binoculars or a telescope until you find the objects that you're looking for. Andromeda is pretty large. She's about the same size in the sky as the moon, at least across. So you can sort of test that out by, especially on a night when the moon is out, look at the moon and then look over to Andromeda. Just make sure you close your eyes a little bit in between and let your eyes readjust because the moon is much, much brighter than this galaxy. The last thing that I want to show you is one more time, I'll show you how to find the center of our galaxy, Sagittarius A Star. Again, not a whole lot to look at here visually, but this is an interesting piece of astronomical history because this source was actually discovered in 1931, before we even had an idea about black holes. Black holes were sort of first studied and postulated in like the 60s and 70s, but this was this extremely bright radio source that we now know was from particles being accelerated around the supermassive black hole and giving off radiation. So here we have the teapot. This is an asterism. An asterism is a group of stars that's well known sort of colloquially, but isn't part of an official constellation. It's just a shape in the sky. So the Big Dipper is a great example of that as well. But I'll show you the teapot of Sagittarius because this is a much clearer sort of group of stars than the whole man holding a bow and arrow. So we've got the handle of the teapot, the lid, and the spout. And then a few degrees out directly in the direction, in the sort of angle that you would be pouring water out of this teapot is the center of our galaxy, Sagittarius A Star. So if you want to, take a look at that part of space, most of the stars in the central bulge are actually obscured by all of this dust, right? We're looking through 26,000 light years worth of just space dust. So it's pretty reasonable to expect that a lot of this light would be obscured. The scientists who sort of probed the structure here were actually working at different wavelengths. So radio light and infrared light is much easier to sort of penetrate through this space dust, meaning that they were able to actually see the stars there. But unless you develop like special eyes or build an infrared telescope, you're basically just going to be sort of looking at the direction of the galactic center. But it's right next to the moon right now, which is pretty fun too. And you've got a bunch of other little star clusters and nebulae around there that are worth a look. So the last thing that I want to do is I want to fly us all the way down to the southern hemisphere. And I want to show you our two satellite galaxies. So these are the large and small Magellanic Clouds, named when Magellan found them on his trip around the world, I believe. So we're going to fly up into the sky and land back down in Sydney, Australia. I figured that'd be a fun place to hang out while we look at the southern hemisphere. And we'll talk about these examples of dwarf galaxies. So these are much smaller than the Milky Way or Andromeda. They don't have a defined center. They're sort of just these big clusters of stars that aren't part of any existing galaxy, and they're just sort of floating around in space. It's actually hard to tell whether they are gravitationally bound to the Milky Way or if they're just passing by. The reason for that is that these objects move extremely slowly. So in the time that we've been able to accurately measure their distance, we haven't been able to exactly measure their motion in the sky. It's a lot easier to tell how quickly an object is moving towards or away from us because we get this red shift or blue shift effect. But telling an object's angular motion in the sky is a lot more difficult. It requires a lot of really precise measurements. So we haven't been able to constrain their velocities exactly to tell whether or not they are sort of in our gravitational orbit or just passing through. So this is the sky at about 2 p.m. in Sydney. I had the sun's atmosphere sort of off, or the Earth's atmosphere off, so we could see all of the dark sky. I'm going to move us forward in time and watch the sunset. You may notice that we've sort of switched direction because we're on the southern part of the Earth now. So north is sort of closer to the equator, which is where I like to put the stuff at the bottom. And then the next thing that I want to do is fly over to the Large Magellanic Cloud, which as you can see is a little bit south of the Milky Way's plane of view, which is why it's not visible in the northern part of the sky. There are a few objects that you may find familiar down here. I'll go ahead and orient us back to the south just so that you see the same sky we were looking at a second ago. We've got, for instance, the moon, which was here and is still here. And then the constellation of Scorpius the Scorpion. And finally, our friend, the teapot of Sagittarius, is still visible, just much higher up in the sky down here in Australia. So let's go ahead and zoom in on the Large Magellanic Cloud. The Large and Small Magellanic Clouds are these two sort of faint smudge-like objects in the southwestern portion of the sky. Take a look at the large one first. And you'll really see what I'm talking about when I say that these dwarf galaxies do not have much of a structure. And additionally, one of my favorite objects to look at is not to look at, I've never been down to the southern hemisphere, but one of the ones on my bucket list and one of my favorite ones to look at in the virtual dome is the Tarantula Nebula. This is the largest nebula in our nearby neighborhood. It's about a third of the entire size of this galaxy. And this was where our most recent supernova that was visible from Earth occurred. This was in 1987. So observers in the southern hemisphere saw this, and it was a blue giant star which went supernova, which is very uncommon. So this was a really interesting phenomenon, and you can see the supernova remnant. You can see images of it with sort of high resolution telescopes now as the gas from that supernova begins to disperse. So this is the Large Magellanic Cloud. And then if we zoom out, we can go travel over to the Small Magellanic Cloud. And that these are only about 200,000 light years away. So comparatively much closer than the Andromeda galaxy, which is why we're able to actually sort of individually resolve some of those stars in the galaxy. While we're looking at the Small Magellanic Cloud, are there any final questions that I didn't get to answer? So again, you can resolve all of those little stars. Each of those sort of fuzzy grains is a star inside of the Small Magellanic Cloud, and then these regions here are nebulae inside of a different galaxy. Elise asks, what software am I showing the simulation on? So this is called Starry Night. This is something that is sold by the people who make planetarium projectors, so SPITs. Different planetariums have their own software depending on who manufactured the projector, but this is something that basically requires you to have a planetarium. I got a copy of this in order to do virtual programming because because our original dome is shut down, but this is sort of pretty this takes up a huge amount of storage space and a lot of computing power, so it's pretty much relegated usually to planetarium computers. There is a free, it's also copyrighted by Spitz, so they I'm amazed that I managed to get a copy. Without the pandemic, they never would have given out copies to the planetarium directors, but anyone doing virtual programming, we got like a trial copy that we can use. So there is, however, a free program called Stellarium, which is fantastic. I actually like it a lot more for stargazing because it's a lot quicker to use. So I will pull it up and I can actually give a quick breeze through tutorial on it if you'd like. You can download this on your phone or computer, or you can just use the web client. And this one is what we have our students in our astronomy labs at Wayne State use. So let me switch my computer over to Stellarium. So this is the sky at, you can zoom in. This is the sky tonight at about, what is that, 10:45 p.m. Let's go back to like 10 around sunset. You can sort of toggle the dials here, and then you can also change your date. So you can go really far back in time if you want to. Like we could go to, let me see how far back this thing will go. Because again, it's just a computer, right? If you figure out the orbital trajectory of all of these things, you can pretty much go forward as far as or back as you want. So let's say I was in 1850 and I was trying to find where Jupiter was. Stellarium would have it directly overhead. And then there's also a lot of cool little bubbles which show off the features that you might find in a star atlas. So this is sort of like an online star atlas, including our favorite M31. And then of course you can click and drag around to change your orientation. You can turn on grids if you're looking for a coordinate system. A lot of the times if you're trying to find, for instance, the Andromeda galaxy, some atlases will give you the right ascension and declination, which are the latitude and longitude in the sky. And then you can use this grid to sort of help figure out where those would correspond to. You can also search for stuff. So let's say I wanted to find where Saturn is. It looks like it's below the sky right now. It's not in our time. I'll jump back to I'll refresh the sky and go back to today. Tonight, Saturn is actually pretty close to Jupiter. So if we looked for Saturn tonight, it would show us that in a couple of hours, it's going to be directly on the horizon. So super nice observing tool. Definitely a lot more user-friendly than the software I was using. The reason that we use this one is because this is actually designed to be projected up onto the dome. So you can do a lot with it in the planetarium space. But yeah, both are great. And this one just happens to also be free. Any other questions? No? All right, let me check to make sure that I didn't miss anybody's during the talk. No, it looks like I was able to cover pretty much everyone's. These were some fantastic questions, you guys. Thank you so much. And yeah, keep your eyes peeled for the James Webb Telescope Week. We're planning some stuff right now. It's going to be really fun in lieu of doing things in person. I think that, you know, live virtual programming is always great because then we can do questions and answers. So thank you all so much. If you're interested in learning about the stellar evolution stuff that I talked about, I'm going to be giving a talk on stellar evolution next month at the beginning of July. This is open. It's run by it's part of the Wayne State Community's programming, but we're open to RSVPs from people who aren't affiliated with Wayne State as well. So Jennifer, do you mind if I drop the link to the calendar for that in case people want to see?
No, that would be great. Thank you, Ethan.
Excellent. So we have a whole tab on our events page. Right now, the show that I'm giving this week is actually the Galaxies show. So a very similar version to this, but probably with less time for Q&A because it's more people. So if you really want to see the Galaxies show again, or you know somebody who missed it, you're welcome to sign up for that. And then I'll be publishing the Stellar Evolution talk later on, probably this week for July. And then my last, I'm going to give another show in late July. I'm not sure which topic I'm going to give it on. I'm torn between talking about black holes or the moon. So we'll see which one I end up doing, sort of based on interest at the solar system or at the Stellar Evolution show. So with all of that said, if there are no other questions, thank you all so much for the great questions and for the nice feedback. And I hope to see you guys soon. Take care, everyone.
Yes, thank you everyone for coming, and thank you so much, Ethan.
Absolutely, anytime.
Great program.